Welcome back. Let's look at some examples involving unit vectors. Alright, so here's our first example. We want to write the following vectors as the linear combination of the standard unit vectors I and j and find their slope. Alright, so we have three different vectors here, vector A, vector B, and vector C. They are all position vectors, or vectors in component form that we want to rewrite in a different way. And we're going to do that by using the standard unit vectors I and j. Now, if you need a quick refresher, the standard unit vectors I and j look like this. Unit vector I is equal to the vector 1, 0, and unit vector j is equal to the vector 0, 1. All right, so these are unit vectors because their magnitude, or their length, is 1 if you were to calculate the magnitude of these vectors by taking the square root of the sum of their components squared. You would just get 1. And I is the standard unit vector for the x direction, and j is the standard unit vector in the y direction. All right, so you can use vector I to describe the x direction of a vector, and you can use j to describe the y direction of a vector. Okay, so if we do that for our first vector here, vector A, we can rewrite this vector using these standard unit vectors. And so here's what that looks like. Vector A is going to be equal to its x component of 4, so I'll write down 4, multiplied by the standard unit vector in the x direction, which is I. So I'm going to write that vector I. And remember that when you write your unit vectors, you want to use this little hat notation instead of this standard vector notation. All right, the hat indicates that it is a unit vector. It has a magnitude of 1. All right, so that describes the x direction of our vector, but now we want to add that to the y component of 7, so we'll have 7 times the standard unit vector in the y direction, j, and so I'll write j. All right, and this right here is another way to represent vector A, but as a linear combination of the standard unit vectors I and j. Now, the reason that this is true, the reason why this is equal to this, is because if we use these definitions of I and j, here's what this looks like. This would be equal to 4 times vector I, which is 1, 0, and then we'd be adding that to 7 times vector j, which is 0, 1. If we perform scalar multiplication here, we'll have 4 times 1, 0 and 7 times 0, 1. We multiply 4 by both of those components and multiply 7 by both of these components. We'll have that this is equal to 4, 0 plus 0, 7, right? 4 times 1 is 4, 4 times 0 is 0, 7 times 0 is 0, 7 times 1 is 7. And then if we add these two vectors together using vector addition, we add the x components and the y components, and we will get 4, 7, right? 4 plus 0 is 4, and 0 plus 7 is 7. And this is the same exact vector we have right here, which is vector A. And so this is a valid way of rewriting vector A. It's the same exact thing, just written differently. Okay, so that's what we're doing when we rewrite our vectors as the linear combination of the standard unit vectors I and j. We're not changing the vectors in any way, we're just rewriting them differently. Okay, so now following that same pattern for our other two vectors, vector B will be equal to its x component of -1 multiplied by the standard unit vector in the x direction, which is I, and then we'll add that to the y component of 3, so we'll have 3, multiplied by the standard unit vector in the y direction, j. All right, now we can simplify this a little bit. Typically, we don't write 1 as a coefficient of a value, so I'm just going to rewrite this to look like this. We'll have -I plus 3j. And that is the linear combination of the standard unit vectors that makes up vector B. Okay? The components of B just become the coefficients of I and j, and we add them together. Now, if we look at our last vector here, vector C, let's write vector C as a linear combination of our standard unit vectors. We'll start off with the x component, which is 1. And once again, we don't really write a coefficient of 1. So we're just going to have 1 times vector I, which is just I. And then we'll add that to our y component times the standard unit vector in the y direction, which is j. So we'll have negative 8 times j. So I'll write that. We'll have negative 8 times j. And then to simplify, that's going to be equal to I minus 8 times j. All right, adding a negative number is the same as just subtracting it. And so this is the linear combination of standard unit vectors that represents vector c. Okay, so now we completed the first part of this example. We have rewritten all of these vectors using the standard unit vectors, but we also want to find the slope of these vectors. And to do that, all we have to do is take the coefficient of j and divide it by the coefficient of I. Because the coefficient of j represents the y component and the coefficient of I represents the x component. And remember that slope is rise over run, or the y direction divided by the x direction. And so the slope for vector A will be 7 divided by 4, and that doesn't really simplify. So that is the final answer for vector A. The slope of vector B will be equal to 3 divided by negative 1, which results in negative 3. And so that is the slope of vector B. And then for vector C, the slope will be equal to negative 8 divided by 1, which just gives us negative 8. And so negative 8 is the slope of vector C. And so that's it for this example, but one thing that I do want to note here is that since all three of these vectors have different slopes, we have 7/4, negative 3, and negative 8, since those are all different slopes, we can conclude that these three vectors are not parallel to each other. All right, because parallel vectors will always have the same slope. So since the slopes are different, these vectors are not parallel. Okay, just thought I'd mention that because sometimes you might come across a problem that might also ask you if any of the vectors are parallel. Let's take a look at another example. All right, so next up we want to find the unit vector in the direction of vector v and show that its length is 1. And our vector v is the position vector of the point 5, 9. All right, now in order to solve a problem like this, in order to find a unit vector in the same direction of a position vector, you need to know the following formula. The unit vector that we want to find will be equal to the position vector v divided by its magnitude, all right, or the length of that vector. And remember that when you denote your unit vector, like I am right here, that you need to use that hat notation. Okay, and really what this just becomes is a scalar multiplication problem. We're just going to have 1 divided by the magnitude of v multiplied by vector v. All right, so now if you want, feel free to pause the video and try to find this unit vector yourself first. And then once you find it, you can play the video and see if you get the same answer that I do. All right, so feel free to go ahead and try it first. But here's how we'll find this unit vector. The first thing that you want to do is find the magnitude of vector v. All right, so the magnitude of vector v is going to be equal to the square root of the sum of the components squared. All right, so that will be 5 squared plus 9 squared. And now if we simplify, 5 squared is 25 and 9 squared is 81. So this is equal to the square root of 25 plus 81. And 25 plus 81 is 106. So this is equal to the square root of 106. And the square root of 106 is in its simplest form. It cannot be simplified any further. 106 doesn't have any factors that are perfect squares, so I'm just going to leave it in this form. So now what we want to do to find our unit vector is divide vector v by that magnitude, right? The square root of 106 is the magnitude of vector v. So here's what we'll have. The unit vector that is in the same direction as vector v will be equal to 1 divided by the square root of 106 times vector v, which is the position vector 5, 9. So we're going to have 5, 9. Okay, and so now all we have to do is multiply this scalar multiple by both of the components of this vector. So if we do that, this will be equal to 5 divided by the square root of 106, and then 9 divided by the square root of 106. And that will be the unit vector in the same direction of vector v. All right, so we found the unit vector, but we also want to show that its length is 1, right? Because a unit vector has a magnitude or a length of 1. So we want to make sure that that's true for this unit vector that we just found. So let's test that out. if we take the magnitude of vector u, that will be equal to the square root of the sum of the components squared. So we'll have 5 divided by the square root of 106 squared plus 9 divided by the square root of 106 squared. And if we simplify, that will be equal to the square root of 25 divided by 106 plus 81 divided by 106, right? Because if we square this quantity, 5 squared is 25, and the square root of 106 squared just becomes 106. If you square a square root, you just get the value inside the square root back. And in the same way, if you square this quantity, 9 squared is 81, and the square root of 106 squared is also just 106. So now we have two fractions with common denominators, so we can add their numerators together, and 25 plus 81 is 106, so this is equal to the square root of 106 divided by itself, and anything divided by itself is 1, so this is just the square root of 1, which of course is equal to 1. And so the magnitude of vector u is 1, which means that it is indeed a unit vector. Okay, let's take a look at another example. All right, so next up we have a slightly more complicated example. It's really going to test our knowledge of unit vectors. We want to find the vector v with a magnitude of 5 and the same direction as vector w, which is the position vector of the point -1, 2. All right, and so how do we go about solving a problem like this? We want to find a vector with a particular magnitude in the same direction as another vector. Well, in order to solve this problem, what we need to do is first determine what the direction of vector w is, right? In order to even find a vector with the same direction as vector w, we need to know what vector w's direction is. And the way that we find that is by finding the unit vector that corresponds to vector w. All right, because essentially a unit vector describes the direction of a vector. All right, so when you think about unit vectors, you want to be thinking about direction. So let's do that. The first thing that we should do here is find the direction of vector w. So we want to find a unit vector for vector w. So what we're going to do is take 1 divided by the magnitude of vector w and multiply it by vector w. Or in other words, we're dividing vector w by its magnitude, right? This is the same exact formula that we used in the previous example, except we're using it for a different vector. So let's do that. We first need to find the magnitude of our position vector. So let's do that on the side here. We want to find the magnitude of vector w. That will be equal to the square root of the sum of its components squared. In this case, the components are -1 and 2. So we'll have -1 squared plus 2 squared. And if we simplify, this will be equal to the square root of 1 plus 4, right? -1 squared is 1 and 2 squared is 4. 1 plus 4 is 5, so the magnitude of vector w is the square root of 5. So our unit vector for vector w will be equal to 1 divided by the square root of 5 times vector w, which I'm now going to replace with this right here, what it's equal to. So we'll have -1, 2. And now we just need to perform scalar multiplication and multiply 1 divided by the square root of 5 by both of the components. All right, so if we do that, this will be equal to this vector. We'll have -1 divided by the square root of 5, 2 divided by the square root of 5. All right, so we just multiplied 1 divided by the square root of 5 by -1 and by +2. So this right here is the unit vector that corresponds to vector w. This gives us the direction of vector w. And so if we want to have a vector v with a particular magnitude in the same direction as vector w, all we have to do is multiply that magnitude by the unit vector. All right, and let me explain why this makes sense. If you take a look at this formula right here, if we were to solve for vector w, we would need to multiply both sides by the magnitude of vector w. So another way that you could write that formula is that vector w is equal to the magnitude of vector w times the unit vector. And the reason that's important to realize is that vector w, a position vector, is defined by its magnitude multiplied by the unit vector, or the direction, right? The vector is defined by its magnitude and its direction. So if we want to find vector v, we should multiply its magnitude by that same unit vector, right? If we want to find a vector with the same direction as vector w, we just take that direction from vector w and multiply it by the magnitude of vector v. I hope that makes sense. All vectors are defined by a magnitude and a direction, and so we're taking the direction from one vector and using it to find another vector with that same direction, but a different magnitude. All right, so if we perform this operation, vector v will be equal to its magnitude times a unit vector, and its magnitude is 5, so we'll have 5 times the unit vector, which we have right here. So we're multiplying 5 by -1 divided by the square root of 5, comma 2 divided by the square root of 5. And so if we multiply 5 by both of these components, we will find that vector v is equal to -5 divided by the square root of 5, comma 10 divided by the square root of 5. All right, now you could leave this vector in this form, but we can simplify it a little bit if we rationalize our denominators. So let's do that real quick. I'm going to do that over here. We will have that vector v is equal to the following vector. If we rationalize both of these components, all we're doing is multiplying the numerator and denominator by the square root of 5. We're just trying to eliminate that square root or that radical from the denominator of each component. And so what that will give us is -5 square roots of 5 divided by 5, and then 10 square roots of 5 divided by 5. Right? If we multiply both of these components by the square root of 5 divided by itself, we multiply both the numerator and denominator by the square root of 5, so we have -5 square roots of 5, and then in the denominator, the square root of 5 multiplied by itself is just 5. And then for the other component, we have 10 times the square root of 5, and then the square root of 5, once again, multiplied by itself, gives you 5. All right, so now we can simplify the components. This 5 and this 5 will cancel out. 5 divided by 5 is just 1. And then we have 10 divided by 5, which is just equal to 2. So vector v is equal to the negative square root of 5, comma, 2 square roots of 5. And that is the final answer to this problem. This is the vector v that has a magnitude of 5 and the same direction as vector w. Okay, all we did was find the direction of vector w by finding the corresponding unit vector, and then we multiplied that unit vector by the magnitude of vector v. Okay, let's take a look at another example. Hey there, real quick, before we take a look at the next example, if you find my tutorial videos here at JK Math to be helpful and you want access to more content such as exclusive bonus videos and dark mode versions of my videos, I'd invite you to check out my membership site, JK Math Plus, where all of that content is available. To learn how to join and see a full list of everything you'd get access to as a member, you can head over to jkmathematics.com/plus. I'll have a link for that in the description of this video. Okay, so if you're interested in becoming a member, feel free to check that out. It's a great way to support me and the tutorials I make, as well as a great way for you to learn math better. But for now, let's get back to the video and take a look at the next example. All right, so our next example is similar to the previous example, but it takes it one step further. We're adding another step into the mix to make things slightly more difficult. But really what this problem is doing for us is combining pretty much everything we know about vectors computational-wise up to this point into one problem. And so this is a really good test to see if you know what you're doing with vectors. All right, but let's read the problem here. If vector A is equal to -2i plus 4j, and vector B is equal to I plus 3j, find vector v, where the magnitude of vector v is equal to 2, and where vector v is parallel to the following vector, 2 times vector A minus 5 times vector B. All right, so this seems really complicated, right? It's one of those problems where at first you're not really sure where to start. But what you have to keep in mind is the end result. What do you want to end up with? In this case, we want to find a vector v with a particular magnitude that is parallel to this vector that is defined by these two vectors. All right, so the first thing that we should probably do is just determine what this vector is. We should multiply 2 by vector A and subtract 5 times vector B. I'm going to define that vector to be vector W. So I'm going to say that vector W is equal to 2 times vector A minus 5 times vector B. All right, and so what that looks like is this. We're going to have 2 times negative 2I plus 4j, and then we're going to be subtracting 5 times I plus 3j. All right, so I just replaced both of those vectors with what they're equal to, right? These are what these vectors are equal to. That was given to us in the problem. So now let's simplify. We're going to be multiplying 2 by both of these terms. And so 2 times negative 2 is negative 4. So we'll have negative 4I plus 2 times 4j. That will give us 8j. And then we're going to be subtracting 5 times both of these terms. So 5 times I will be 5I, and then we'll add that to 5 times 3j, which will be 15j. Okay, now if we simplify, we need to distribute this negative through this quantity. So this will be equal to negative 4I plus 8j, and don't forget the hats, minus 5I minus 15j. Okay, and now at this point what we want to do is combine our like terms. We want to combine our I terms and combine our j terms, right? This is just like adding the x and y components of our vectors together when we do vector addition. We have our x components, which are the coefficients of the I vectors, and our y components, which are the coefficients of the j vectors. All right, so negative 4 and negative 5 become negative 9. So this is equal to negative 9I, and then positive 8j and negative 15j will become negative 7j. Okay, and so negative 9I minus 7j is what vector w is, or in other words, it's what this vector right here is. All right, so just so we don't forget, that is equal to vector w. Okay, so now that we have vector w, what can we do with it to find vector v? Well, remember, we want to find vector v such that it is parallel to that vector, vector w. In other words, we want vector v to have the same direction as vector w. This is just like the previous example. If we want to find a vector that has the same direction as another vector, we just need to find the unit vector for that vector and then multiply the magnitude of the new vector by that unit vector. All right, and the reason I came to that conclusion is because when two vectors are parallel, they're pointing in the same direction. They're going to have the same unit vector. So we need to know what the unit vector for w is, and then we'll use that to find vector v. All right, so the unit vector for vector w can be found by taking 1 divided by the magnitude of vector w and multiplying it by vector w, right? Another way to think of it is just taking vector w and dividing it by its magnitude. So let's calculate the magnitude of vector w, and in case you're not quite following what this vector exactly is, we could rewrite it using the other form of a vector, and it would look like this, negative 9 comma negative 7, right? Negative 9 is the x component and negative 7 is the y component. So this is another way to express vector w. And so if we use those components, we can find the magnitude of vector w. The magnitude of vector w will be equal to the square root of the sum of the components squared. So we'll have negative 9 squared plus negative 7 squared. Negative 9 squared is 81, and negative 7 squared is 59. So this is equal to the square root of 81 plus 49. And 81 plus 49 is 130. So this is equal to the square root of 130, which does not reduce any further. 130 does not have any factors that are perfect squares. So we're going to keep it in this form. And so if we want to find the unit vector for vector w, we will take 1 divided by that magnitude of the square root of 130 and multiply it by vector w, which is this vector right here. Now I'm going to choose to use this form of the vector this time around instead of this form. You should try to get used to working with your vector in terms of I and j, because we're going to work with that a lot later on in Calculus 3. So I'm going to try to get in the habit of doing that now. So we're going to be multiplying by negative 9i minus 7j. All right, and so if we multiply this by both of those terms, we will find that the unit vector is equal to negative 9 divided by the square root of 130 times I minus 7 divided by the square root of 130 times j. All right, and so that right there is the unit vector that corresponds to vector w. All right, and so that describes the direction of vector w. So if we want to find vector v with this magnitude and the same direction as vector w, it's parallel to it, we want to take this magnitude and multiply it by that unit vector. All right, once again, just like with the previous example, I'm going to write this out because I want to make sure that this makes sense to you. If you take this formula right here, the formula that we use to find this unit vector, and we multiply both sides by the magnitude of vector w, what that would tell us is that vector w is equal to the magnitude of vector w multiplied by the unit vector. So vector w is defined with its magnitude multiplied by its direction, the unit vector. In the same way, vector v, the vector that we want to find, would also be defined by its magnitude multiplied by a direction, a unit vector. And so if we want vector v to have the same direction as vector w, we want them to be parallel, we're going to use that same unit vector and multiply it by the desired magnitude for vector v. So let's do that. Vector v will be equal to 2 times the unit vector that we just found of -9 divided by the square root of 130 times I minus 7 divided by the square root of 130 times j. And so if we multiply 2 by both of those terms, we will find that v is equal to -18 divided by the square root of 130 times I minus 14 divided by the square root of 130 times j. All right, we just multiplied 2 into the numerator of both of those terms. And so this right here, that is one form of a correct answer to this problem, but you could also use the other notation to represent a vector. And so let me show you that real quick. Vector v would also be equal to -18 divided by the square root of 130, comma, -14 divided by the square root of 130. All right, so you could also use this notation if you wanted. They're the same answer, just expressed differently. Okay, let's take a look at one more example for this video. All right, so for our last example, we want to find the following vectors given their magnitude and angle that they make with the positive x-axis. All right, so this is going to use a slightly different definition of the unit vector that would make up a vector. All right, so if you've gone through the previous examples, you know that I've been saying that a vector is equal to its magnitude times a unit vector. And I talk about this in the lesson video for this topic, but another way that you can represent this unit vector right here is with the following vector. It will be equal to cosine of theta, comma, sine of theta, where theta is the angle between the vector and the positive x-axis. Or another way that you could write this is cosine theta times I plus sine theta times j. All right, so either way, multiplying the magnitude of a vector by this unit vector will also give you the vector that you're trying to find. So for these three vectors, vector A, vector B, and vector C, we are given a magnitude and an angle that they make with the positive x-axis that we can use to find those vectors. All right, so let's start with the first one here. What's this going to look like? Well, vector A is going to be equal to its magnitude multiplied by a unit vector that we will find by using this angle. Now, I'm going to recommend that you don't work with angles in degrees. I think it's always going to be better to work with them in radians. That way, if you're using a calculator, you don't need to be constantly switching between using degrees and radians. You can keep it in one mode and not have to worry about making mistakes. Another reason I recommend working with radians is typically we know those values better. I think at this point, now that you're in Calculus 3, you're probably more familiar with evaluating sine and cosine of different angles in radians. Now, the angle of 0 degrees is pretty easy. That's actually the same as 0 radians, because if you don't remember, the way you can convert from degrees to radians is to take your angle and multiply it by pi divided by 180. All right, so if we multiply 0 by pi divided by 180, you're still going to get 0. And so if our angle is 0 radians, here's what vector A is going to be equal to. We will have that magnitude of 3 times the unit vector, where we'll have cosine of 0 times I plus sine of 0 times j. All right, we took that angle of 0 radians and plugged it in to cosine and sine, and that makes up the unit vector, or the direction of vector A. So now if we simplify, this will be equal to 3 times cosine of 0 times I. Cosine of 0 is equal to 1. So we'll have 1 times I. So really we just have I. And then that will be added to sine of 0 times j. And sine of 0 is just 0. So we're going to have 0j. All right, now multiplying 3 by both of these terms will give us that vector A is equal to 3I plus 0j, right? 3 times 1 is 3, and 3 times 0 is 0. And so this right here would be vector A, but you could also write it to look like this. It would be the same thing as 3, comma 0. All right, and you could also rewrite this by just omitting the j term. You don't even need that since it's 0. You could just rewrite this to be 3I. That's another way that you could write that as well. All right, so all three of these are acceptable answers. It depends on what notation you want to use and how much you want to simplify. Okay, but now let's work on the next vector, vector b. Vector b has a magnitude of 2 and an angle of 120 degrees with the positive x-axis. So vector b will be equal to the magnitude of 2 times cosine of that angle times I plus sine of that angle times j. Now this angle is currently in degrees, so we want to convert it to be in radians, or at least that's how I like to do it. We can find the equivalent of 120 degrees in radians by multiplying it by pi divided by 180. So if we do that, I'm going to multiply by pi divided by 180. 120 divided by 180 is going to give you 2/3. So our angle will be equal to 2 pi divided by 3. All right, so that's going to be our angle in radians. I'll write that down here in radians. So we'll write that in to cosine and sine. And cosine of 2 pi divided by 3 is negative 1/2. So if we simplify, this will be equal to 2 times negative 1/2 I plus sine of 2 pi divided by 3. That's equal to the square root of 3 divided by 2. So we'll have that times j. And then if we distribute this 2 through this quantity, this will be equal to negative I plus the square root of 3j. Right? 2 times negative 1/2 is negative 1. So we just have negative I. And then 2 times the square root of 3 divided by 2, those 2's will cancel out and just leave you with the square root of 3. And so this is vector b, or at least one way to express it. Another way to write it would be like this. We'd have negative 1 comma the square root of 3. The x component and then the y component. Okay, so that's vector b. Let's move on to our last vector, which is vector c. For vector c, we want to have a magnitude of 4 and an angle of 150 degrees with the positive x-axis. Now the first thing I'm going to do here is convert this to be in radians. So we're multiplying by pi divided by 180. And if we do that, that will give us an angle of 5 pi divided by 6 radians. All right, 150 and 180 are both divisible by 30. 150 divided by 30 is 5. 180 divided by 30 is 6. So we get 5 pi divided by 6. Okay, so that's going to be our angle. So vector c is going to be equal to its magnitude of 4 multiplied by the unit vector, where we use this angle of 5 pi divided by 6. So we'll have cosine of 5 pi divided by 6, I plus sine of 5 pi divided by 6, j. And I just barely fit that all in there. I know it's not very easy to read, but that is a j right there. And if we simplify, cosine of 5 pi divided by 6 is the negative square root of 3 divided by 2. So this is equal to 4 times the negative square root of 3 divided by 2 times I plus sine of 5 pi divided by 6, which is equal to 1/2, and that's multiplied by j. And so if we simplify, we multiply 4 by both of these terms. This will be equal to negative 2 square roots of 3i plus 2j, right? If we multiply 4 by this term, 4 divided by 2 is 2. So you're just going to be left with that 2 in the numerator. So you have negative 2 square roots of 3, and then 4 times 1/2, of course, is 2. Okay, so this is one way to express vector c, but another way that you could write it is like this. You'll have negative 2 square roots of 3 comma 2. All right, so that's another way that you could write vector c. And so with that, we have now completed this example. We have now found all three vectors using the given magnitudes and their angles that they make with the positive x-axis. Okay, and so this was the last example for this video. If you do want to see some more examples, I do have more on my membership site, so feel free to look into becoming a member if that interests you. If you have any questions, feel free to leave those in the comments, but if you don't have any questions, this is all I had for now, so I will see you next time.